In the last video, we discussed how when the system gains energy, it comes from the surroundings in the form of heat, for example, here. And when the system loses energy in the form of heat, it's lost to the surroundings. Well, that tells you something. It tells you that energy or heat is not being created out of nowhere. System is not gaining energy or heat within itself from nothing. There is a source, and the source was the surroundings here. Similarly, if the surrounding is gaining something, it comes from the system. That is the basis of the first law of thermodynamics. The first law of thermodynamics is stated in many ways. Here we are stating it as energy of the universe is constant. Another way of stating this is energy can not be created, neither can it be destroyed. Either case, it means the same thing. Energy is there and we cannot create it. It's either gained by the system from the surroundings or lost to the surroundings from the system. It is constant. The amount of energy in the universe is constant. So that means that since humans have been on this planet, however amount of energy we have used, it's still the same amount of energy in the entire universe. We have not created some new energy. When you go, when we are using gasoline, for example, uh, to go from somewhere in our car to another place, and we are using energy, but if we are using the energy, is the energy used up, it's gone, it's destroyed? No, because the energy of the universe is constant, energy cannot be destroyed. Neither did we create energy when we were using gasoline. All we did was convert the energy from one form to the other. We made it less usable for us humans when we used up gasoline, but still, energy of the universe remained constant. This law is also called the law of conservation of energy. We looked at another law called the law of conservation of mass when we were balancing chemical equations. So, when energy is gained, it's gained from the surrounding, and when energy is released to the surroundings. Here is a chemical reaction. Since we are chemists and we are going to deal with thermodynamics as it pertains to chemistry, here is the reaction. A compound AB and CD, both of them are undergoing double displacement, and A is going with D and C is going with B. So bonds are being broken here. The bond between AB is being broken and the bond between CD is being broken. And at the same time, a new bond is being made. The bond between AD is being made and the bond between CD is being made. When it comes to chemistry, energy that is involved is generally called chemical energy. Chemical energy is the energy that's stored within the bonds. The bonds themselves contain energy, and when we say a reaction is happening, we say that bonds are breaking and new bonds are being made. Whenever we have to break bonds, we need to supply energy. So in order to break this AB bond and this CD bond, energy must be supplied. And whenever a bond is made, energy is released. So when we say we are supplying energy here, we are supplying our energy to this system, and then eventually the system is releasing energy as well. How is the supply of energy coming from? It's coming from the surroundings. We are doing something to this mixture of A, B and CD, where energy is absorbed from the surroundings by this system, and then it breaks the bonds within the system, and when new bonds are made, our system releases energy to the surroundings. Okay, so here we broke the bonds and here we made the bonds. Making of the bonds releases energy, breaking of the bond requires energy. But we don't treat this reaction into two different parts as if breaking and making. We instead take the net change. So whenever you are doing your monthly tally of whatever money is in your bank account, for example, you may count how much salary is flowing in the form of money, and then how much money is flowing out due to paying of bills. Well, the net change is what matters, whether you are in net positive or net negative. Similarly, how much energy is required to break the bonds added or compared with the amount of energy released when making the bonds. That tells us whether we have a net release of energy or a net gain or requirement of energy. If there is more energy that's released than required, then there will be a net release of energy. And such a chemical reaction is called an exothermic reaction. When you carry out such a reaction, that reaction releases energy to the surroundings. Okay? So think about a bomb exploding. A bomb exploding releases a lot of energy. It might require a little bit of energy in the beginning for us to do whatever the bomb requires initially for it to explode. But then when it does, it releases a lot of energy. So that's an example of an exothermic reaction. Exothermic means exo means out and thermic means heat. So heat going out of our system. But remember, the amount of energy released when bonds are made is greater than the amount of energy required when bonds are broken. That is what makes a reaction exothermic. If the opposite was to happen, where the amount of energy required to break the bonds was greater than the amount of energy released when bonds are made, then there is a net requirement of energy, and energy must be supplied to the reaction as a net in order for the reaction to happen. We do this kind of reactions also whenever we are cooking food, for example, and we are trying to tenderize meat by boiling it in water or anything else. We are supplying energy from our heating stoves. We do not cause the meat uh, to actually end up releasing energy at the end, but we just supplied it energy and a lot of bonds were broken, and that tenderized the meat or vegetables or whatever you are cooking. And so there was a net gain of energy from the surroundings to by the system. That situation is called endothermic reaction. Whenever reaction requires a net supply of energy or heat, endo means entering inside the system, thermic means heat. Now we can show this in a diagrammatic form shown here. Here we are placing our reactants on the left and products on the right. This is also known as an energy diagram, and you can sort of see what's going on. The more complex energy diagrams also exist, but this is a simpler version of it. And in this diagram you have reactants on the left placed up here and products here. Now look at the y-axis. This is the x-axis. X-axis denotes the progress of the reaction. Y-axis denotes the something called enthalpy, which for our purposes at this moment we will think of this as just energy. And reactants are placed very high in terms of internal energy they have, while products are placed down here. When the reactants are changing into products, products have much less energy within them than the reactants. What does that mean? It means that products, when they formed, there was an ultimate net release of energy that happened in this reaction. And as we know that in a net release of energy reaction, we have that reaction being called an exothermic reaction. So here in this diagram, in the top portion, part A, we are depicting an exothermic reaction when we place the products below the reactants. Since in this reaction energy is being released, we can think of energy as being product, as another product that's not a chemical but a product of the reaction nevertheless. So if these reactants were methane gas, CH4, and oxygen gas producing carbon dioxide and water, the product of this reaction in terms of energy is heat, 211 kilocalories. Notice how it's placed on the right side of the equation. On the other hand, if you have a reaction that requires us to supply heat, a net gain of heat is required, then that heat is placed on the left of the arrow on the reactant side, because now it is a requirement for the reaction. So decomposition of ammonia into nitrogen gas and hydrogen gas, well, the products nitrogen and hydrogen are placed higher up on this energy diagram. They have a net higher energy than the original reactant, and that energy came from the surroundings where we supplied it with where we supplied ammonia with 22 kilocalories of heat. Kilocalories, by the way, is how we measure heat. There is another unit as well called kilojoules, which we will investigate further. Now, what is enthalpy? Enthalpy in this case represents heat. The definition of enthalpy can be very complex, but simply speaking, what we are going to do is consider heat energy as enthalpy, and change in enthalpy shown here by writing this symbol. This symbol is called delta. It's a triangle. It's called delta. It means change. Change in enthalpy is the difference in the energy of the products and the reactants. And so here is the formula for the change in enthalpy for on a reaction, or change in the heat of a reaction. Enthalpy of the products, delta H of the products minus the delta H of the reactants. That's what gives us the change in enthalpy of a reaction. Whenever we apply this reaction and we subtract the delta H of the reactants from the products, and we get our value with a negative sign, that tells us that we have an exothermic reaction. Why would that be the case? Because if the delta H of the products here is less than the delta H of the reactants, that means there was a net loss of energy. The products, when the reactants reacted, they lost a lot of energy forming the products. So the products have very low energy within them. Hence, the delta H of the products is lower than that of the reactants, and we will get a negative value there. And so that's what it tells us, that it's a exothermic reaction. On the other hand, if the value is positive, that tells you it's an endothermic reaction. So those are the two ways we can find out whether a reaction is endothermic or exothermic. Let's look at these reactions and classify them as being exothermic or endothermic. Okay, so the first one is just a sentence: fuel oil is burned in a furnace. Now, because it's a fuel oil, what does it do? It provides heat. So if the whole reaction of burning the fuel oil is to supply heat to the surroundings, that means it must be an exothermic reaction. Whatever is the amount of heat, we do not know unless we actually do some measurements, but we can bet that the sign for it would be a negative sign. Here is another reaction: C6H12O6 gets converted into C2H5OH. This is glucose turning into carbon dioxide and alcohol, ethanol, in a reaction called fermentation. Notice the delta H given here, it's negative 16 kilocalories. Because the sign is negative, that means this is an exothermic reaction. There is a net loss of heat. As the reactant gets converted into the product, there is a net loss of heat from our system here of this reactant, and the product releasing that heat to the surrounding, and the amount of heat is negative 16 kilocalories. If we had to write this negative 16 as part of the equation here, as we saw previously here in this form, either on the right side or on the left side, where would we write it? Oops. Would we write it on the left side or the right side? Is heat here the product or a reactant? This is the amount of heat that is being produced. Whenever it's negative sign, it means it's being produced. And so if you were to write it as one of the two, reactant or product, we would write it on the product side, and we would write it as plus, add, so just like we have plus 2 CO2, then we would continue writing plus 16 kilocalories. Yep. Don't confuse that plus sign with this sign. When we write it separately, we are trying to state that this is exothermic. But when we write it here as part of the equation, plus 16 kilocalories, just the fact that we wrote it on the right side of the equation tells us that it's exothermic. Similarly, here in this reaction of dinitrogen pentoxide with water producing nitric acid, there is a net release of energy by 18.3 kilocalories, and hence that's an exothermic reaction as well.